Welcome to this talk on stochastic Euler equations via geometry. This is joint work with Mario Morelli from Milano and Klaas Modin from Gothenburg. In this talk, I shall explain how certain stochastic PDE can be studied using infinite dimensional geometry. The idea is as follows. So usually when you want to study elementary properties of partial differential equations, this is at least harder than to study for example, existence and uniqueness of solutions for ordinary differential equations. Also, smooth parameter dependence of a partial differential equation might be tricky. And for ordinary differential equations, there's a standard theory which tells you if your right-hand side of the equation is nice, then you get all these things, at least locally. And the idea is now, well, perhaps we can, at least for certain PDE, rewrite the PDE or relate it somehow to an ordinary differential equations, where the properties of the ordinary differential equation give us some structure for the solution or some information of the solution of the PDE. And indeed, for certain PDE, usually arising in hydrodynamics, there is a method to do this, which goes back to a paper by Arnold from '66 and was later then worked out by Eben and Marston in '69 for the Euler equation of an inviscous fluid. And they come up with a clever way of relating a PDE of a certain kind to an ODE. However, you pay a price. Obviously, you can't just sort of associate any ODE to your PDE and learn something about the solution of the PDE. So what is happening in this method is you start with a PDE on a finite dimensional domain or finite dimensional manifold, and the associated ODE then typically lives on an infinite dimensional manifold. So you basically go from finite to infinite dimensions, and these hydrodynamic PDE then become geodesic equations on an infinite dimensional manifold. So a geodesic equation is basically connected to some differential geometric objects on the infinite dimension manifold. And our idea is now to basically expand this mechanism in the deterministic setting called by Arnold and Eben and Marston to a stochastic setting. So we want to take a stochastic PDE, associate stochastic differential equations on an infinite dimensional manifold, and go back and forth between the two to learn something about the solutions of the stochastic PDE. Namely, we are interested in uniqueness and existence for stochastic PDE, and we want to establish these results with the help of infinite dimensional differential geometry. Okay, our setting is as follows. We take a compact manifold K of dimension D with a Riemannian metric and a volume form. If you're unfamiliar with this setting, just think of K as some compact bounded domain in Euclidean space, and the Riemannian metric being the usual inner product of Euclidean space. I should mention that our manifold is always allowed to have smooth boundary, but I won't go into details here because it's only getting technical if I want to talk about boundaries. But you can do this, so there's no problem here. And as an example for such a thing, let me formulate Euler's equation for an incompressible fluid. So Euler's equation reads time derivative of a vector field ut. So the subscript t here does not mean another time derivative. It's just a reminder that the vector field is time dependent. So the vector field has a time variable and a spatial variable. So then Euler's equation is d dt ut plus nabla ut equals minus grad of some force. So usually you have the grad of a pressure function here, and then plus some additional forcing terms. Okay, and I should mention here that the choice of Riemannian metric we have here is then informing how these differential operators, so the nabla and the grad, should be interpreted. Okay, also part of the Euler's equations are that we want divergence-free vector fields, and we of course start with some initial condition u0, which is a fixed divergence-free vector field. Now, instead of searching for the vector field ut, which would be the Eulerian point of view for Euler's equation, we can switch to Lagrangian point of view, and instead of solving for ut, we can solve for its flow. So the eta t is again something which eats two variables, time and spatial variables. And if we are not evaluating the spatial variable, we can think of the eta t for some fixed time as a diffeomorphism on the underlying manifold. And the idea is now basically to look at the curve t goes to eta t, where we haven't evaluated the eta in some spatial coordinate. And this curve turns out to be a geodesic for the L2 metric on the volume-preserving diffeomorphisms. So volume-preserving diffeomorphisms, they form an infinite dimensional manifold, and a geodesic can be described by a second-order ordinary differential equation now on the infinite dimensional manifold. So we are seeking to solve the geodesic equation, which is an ordinary differential equation of second order on the infinite dimensional manifold. And Eben and Marston have worked this out in the deterministic setting. They say, okay, let's introduce mappings of Sobolev type with high enough Sobolev index and L2 derivatives. This yields a Hilbert manifold, and then they were able to show that the right-hand side of the second order ODE we are seeking to solve can be shown to be smooth. So they get from the infinite dimensional ODE techniques for Banach space or Hilbert manifolds, they get local well-postedness and continuous parameter dependence of Euler's equations. And we want to extend these techniques to SPDEs of the following form. So I'm writing the equation here as an integral equation. So you have d eta dot equals a drift term, which is determined by the Euler-Arnold PDE. So here we have the drift term associated to the Euler equation of an inviscous fluid. But as I said, there's a whole class of Euler-Arnold PDE, so we can always take another drift term depending or coming from another Euler-Arnold PDE. And then in the first approximation, we have this very easy additive stochastic time noise. So the noise we have is always only time noise. There's no spatial noise here. And so this noise we have is just an additive noise. So it's purely additive, and we expect to be later able to do some more involved noise. But the first formulation is for additive noise, integrated here in Stratonovich sense, since we're on a manifold. And then the theorem is, if we fix this Sobolev index and assume that our noise is in the divergence-free vector fields of high enough Sobolev regularity, so we need Sobolev regularity S plus 2, then the Lagrangian form of the stochastic Euler equation is locally well-posed. That was exactly the equation on the previous slide. However, we were not only interested in the Lagrangian form, but also we want the Eulerian, or the usual form of the stochastic Euler equation. And here the result continues. So if your noise is even a little bit better, not S plus 2, but S plus 4 is needed here in regularity, then this local well-postedness also holds for the original stochastic Euler equation. And clearly this regularity is not optimal. We are actually expecting to get rid of the plus 2 and the plus 4 in the statements using some regularization techniques. And this is also what you would get using standard SPDE techniques. Okay. However, the advantage of why should you do such a thing if it, at least the theorem states it with non-optimal regularity? Well, the whole technique is agnostic of the underlying manifold. So the dimension of your manifold is arbitrary, and also boundaries are allowed. So you can basically, you have a very high degree of freedom of what you're doing there. Okay. Where we are going next with these ideas is the following. So as I said, there's a whole family, the Euler-Arnold family of PDE, which contains, for example, the Kamasa-Holm and the Hunter-Sexton equation, as well as certain shallow water equations. And the idea is to extend the theory for these equations. Then there's a famous no loss, no gain theorem, which tells you that the statement of local well-postedness from the last slide, which actually depends on my choice of Sobolev index, is in reality not depending on the Sobolev index. So if your initial data is good enough, then the solution will be the same for all of the Sobolev index spaces in which it exists. Then obviously one wants a different multiplicative noise, which is more interesting than the purely additive one we had there. And finally, we have some ideas of how to derive from this geometric setting numerical methods, like spectral methods for stochastic Euler's equation. Okay. Well, thank you for your attention. And if you want to have more details on this whole theory and a comprehensive presentation, this can be found in the paper you see here, which is on the archive. Okay, so thank you very much.